Alrighty, so now that we have identified what we need to break down in order to make the best lasagna or solve the best puzzle, we got to have a system that enables us to do that. And so in order to do that, we can't just use a regular computer, or we could, but that's not cool. So what we need is a supercomputer, right? And so there are different components required in order to build a computer that can, make the quickest lasagna or solve a puzzle in the fastest way possible. And so over the years, supercomputers have evolved architecturally and structurally in the way they're connected. The first early supercomputers were the early Cray machines of the 70s and 80s, and those were built mainly vector-based processing systems that were good for hardcore, heavy numerical scientific calculations, right? But as science evolves and different workloads come into play, we need to evolve those systems. And that's what led to what more modern day systems look like, which contains different processing units, CPUs, GPUs, as well as various interconnects, as well as different hierarchies and memory structure as well. So this is kind of the idea of what we say when we talk about the architecture of a supercomputer. And so what do we think about when what do we say when we think we're talking about a supercomputer? Well, we're talking about something that's, generally at least 100 times more powerful than your traditional personal computer or laptop, desktop. And so that's what we say a supercomputer is. It's also called a high performance computing system or scientific computing system. And supercomputers enable us to do different scientific workloads and simulations. And so current supercomputers are considered more generalized for different workloads over traditional early supercomputers. And so modern day supercomputers are constructed in different what you call architectures. You can have a cluster architecture, and so that's going to connect different computers together using some type of cost-effective network and provides for a scalable solution. You can have symmetric multiprocessors or SMPs, and those involve, having multiple processors that share a single memory space for their computation. And then those are able to do frequent communication between those processors more effectively because the memory is shared. And then you have massively parallel processing systems as well. And those are just many processors with their own memory, able to do tasks accordingly based off of those memory requirements. So those are some of the different architectures that we have in a general sense. And so what you want to make sure you keep in mind is that SMP stands for symmetric multiprocessing architecture. And that's going to be what we commonly use within our systems for servers and HPC environments as well. And so that allows for all of those processors to have equal access to memory and input and output for all of those devices. And so with massive memory, that memory is shared by multiple processors to allow for access as needed. Any of the processors, they can do the work required, and that's going to be based off of no matter where its location is in memory. What might be some problems when it comes to being able to access the data you need from memory? If you have to go, let's say you don't remember how to make lasagna, and you go get the recipe for lasagna from the top shelf in your study that's upstairs, and you look at it and then you're like, okay, I know what to do, and then you run back downstairs and you start doing something, and then you're like, oh snap, I forgot, what else am I supposed to do? And then you have to run back upstairs to get it. Why is that a problem?
Latency.
Can you speak up?
Oh, sorry, it takes time, latency.
Yeah, it's going to slow you down because you have to keep going to figure out what the next step is. So constantly having to do things from memory can be very time consuming, especially if it takes the memory latency is long to retrieve that data. So that's another thing about the importance of memory on our supercomputing systems. So with any processor being able to share the memory, that makes for it easy for parallelizing the workloads evenly. So if you have like different loops or different summations and calculations, you can easily parallelize those operations for yourself. And so with this in mind, SMPs allow for, again, better load balancing across different resource contentions and across the different processors as well. Now let's consider cluster architectures. Now cluster architectures, they allow for different racks and cabinets that can be used to do various computations quickly and fast. They're going to communicate through a network connection and allows for programs to be written and divide those computations with the minimal communication. And this can be very beneficial if you have a lot of data intensive workloads that you need to store and collect from and retrieve data from memory. The network connections can sometimes slow you down, but if you can store it in memory, then that gives you more efficient processing. And so most modern architectures that we have nowadays, they're very hybrid in nature. It's more computing, even your localized desktop to supercomputers have gone towards, having different processing units, whether it's a CPU for the central processing unit, GPU, or even now the introduction of quantum processing units as well. So a lot of the state-of-the-art architectures, they're hierarchical and they're hybrid with different computational hierarchies as well as memory hierarchies. So you can think of these systems as having like each node having 32 to 256 cores available to parallelize your workload. So with this type of architecture, most of the time we're going to have memory being shared in those nodes, and that allows for it to appear like a cluster architecture. And we also need to have different mechanisms that we can use to communicate efficiently. So that introduces different parallel libraries like what we're about to talk about after this talk, MPI, as well as OpenMP and even hybrid programming, where you combine those together, and even with other standards like CUDA and other parallel programming environments as well. So let's talk about our system that we have currently at NERSC. And so Perlmutter is named after Saul Perlmutter, and it is a 93.8 petaflop system. When it first debuted, it debuted at number 8 on the top 500. I think we're around number, 18 or 19 maybe now, something like that. But we have a new system on the horizon, Doudna. So 93.8 petaflops is our computational workload or max. What do you think, like the Cray 1 system that I showed from the 1970s? What do you think that peak performance was around back then? Any guesses?
Way less than your phone.
It was less than your phone. What's the peak performance of your typical smartphone? Okay, me either. But the Cray was, I believe, about 70 to 80 megaflops. So we're at 93.8 petaflops. So that's like 1 trillion times slower, okay? And now with so that is just to give you a performance comparison of what 50 years can do. With the Perlmutter, it's very complex system. We have different partitions where there are CPU only nodes available as well as GPU accelerated nodes too. And so over 1,700 GPU nodes and over almost 3,100 CPU only nodes. Again, the CPU only nodes are constructed with just the AMD Milan CPUs. And then our GPU nodes have a combination of one AMD CPU as well as 4 GPUs for accelerated workloads. And also we have a different hierarchical infrastructure for our various storage that we have available. We have our high performance storage system. We have our CFS. We have our Scratch in your home as well. And so these are also connected through different scientific gateways and scientific workflows that allow for collaboration across different labs, different organizations, as well as with different groups as well. So the progression in supercomputing has gotten more towards being more collaborating and how to accelerate workflows versus simulations just being done, in a bubble. You're working on your climate simulation. You don't need to talk to anybody else. Nowadays, it's more collaborative. You might need someone that can process the data more effectively for you. You might need to introduce a new paradigm into your algorithms, or you might need someone that specializes in quantum processing for you as well. So new systems now are built more towards collaboration and accelerating science that way.
Charles, if you're interested, the iPhone 15 Pro is 2 times 10 to the 12th flops.
Okay.
And the Cray one was 8.6 times 10 to the 7th.
Okay,
So-
so you were right, smart. All right, so we have been validated. And so again, Perlmutter is optimized for science, and that way we're gearing up towards the end of the cycle with Perlmutter. And we'll talk a little bit about our future system. But with the different types of nodes that we have available on Perlmutter, they're really aimed at different types of scientific calculations. A lot of processing on GPUs is going to be quick calculations that are not memory intensive. And so that's what makes GPUs able to do specific scientific calculations better than other paradigms. And with CPUs, it can be more general, but it only has 10% of the compute power with the CPU, but it allows for traditional scientific computing that might be a little bit more memory intensive. And that's when that, communication comes into play, where you're running upstairs constantly to get the recipe. So that's kind of the difference in also the structure. And if you remember, or if you don't remember, the first supercomputing Cray systems, they were vector-based. And those are good for, intensive computational calculations, but they're not good for areas outside that domain, which is why we have systems nowadays, our GPUs and CPUs are able to kind of mimic the vector processing within each of the processing units. So that makes it a little bit, our computing is much more generalized than it used to be, aimed specifically towards heavy scientific calculations. And so again, we have different storage available on our systems. CFS, we have Scratch, and we have HPSS as well. And so over the years, NERSC architectures have changed. So Seaborg, the first supercomputer that I got access to when I was a master's student, almost over 20 years ago, was Seaborg and Jacquard, and those were IBM Power 3 and Power 4 systems, I remember. And Jacquard was the first one that incorporated a dual core chip into it. So, back then we were like, oh, wow. And so, and then you have BASI, that was another system that I also used in my master's and part of my PhD as well. So NERSC architectures have steadily evolved, and you'll notice that we've kind of transitioned from, we had IBM and different types of systems to Cray systems. Our current system is also a Cray as well. We've had Edison and Corey as well. So most architectures, again, are hybrid CPU, GPU architectures, again, to keep up on time. So now we are accelerating our scientific systems Again, more towards collaboration, a lot of, AI modeling and training is needed, a lot more collaborative, cross-disciplinary, scientific, results are being done. In order to do that, we made changes and identified our next generation system named after named after Berkeley Lab Nobel Prize laureate Jennifer Doudna, who earned the Nobel Prize for CRISPR technology. So that is typically all of our systems we name after some Berkeley scientist that has won a Nobel Prize, because we just have them laying around left and right, just greatness everywhere. So Perlmutter was named after Saul Perlmutter. Now our next system is going to be Jennifer Doudna. We just officially announced it last month. And so the Doudna system is going to be 10 times more powerful than Perlmutter. And so who knows what type of scale of computing does that bring us into? It's going to be 10 times more powerful than 93.8 petaflops. So that is going to bring us close into the exascale range. So that is 10 times more. So even more scientific, calculations, finding different parallel worlds and all of that stuff. Yeah, that's what we're supposed to be able to do. But we'll see. So Doudna is going to again be a CPU, GPU. This is going to be a Dell-based system. So it is a venture away from our traditional systems that we normally have. Yeah, and again, it's focused on achieving a more collaborative scientific workflow environment, better storage and interconnects as well. So the future is looking bright for scientific computing.